walk the in this protocol block list using the next protocol link. One of these links may be broken because they didn't acquire the in this protocol list lock. So what about stable way for this problem? The right solution will be to use real list head and real list lock. The main problem is that they are not exported. Other problem is that this list is single linked and we can't walk it backwards to find the head. But we can perform static analysis of this.sys driver to find all these variables because they are global, and it's easy to find them by walking this register protocol function. Both of these global variables are used by this function. So if we will enumerate all absolute pointers of this function, we will have a list of variables, and two variables from this list will be our needed ones. We will check every found global variable to be some kind of a pointer to a spin lock by examining the calls to kf require spin lock function. And actually, there exists just one variable which is used as a spin lock pointer, and this variable will be our needed spin lock which protects the list of protocols, and it's called in this protocol list lock. Then we will acquire this the spin lock, and after that we will try to walk every other global variable found in by the static analysis of this register protocol function. Here we will use some tricks to check if this variable is actually a pointer to the list of this protocol block linked list, or it's a pointer to somewhere else by looking into by checking some critical fields of in these protocol blocks, for example. This slide is about usages of in this protocol list global variable. I've shown here a few functions that use this pointer, but you see that none of these functions belong to packet indication code. The conclusion of this slide is that this global variable in this protocol list is not used by the packet indication code at all. So let's see how this open adapter actually registers a filter to the packet indication code. First, it should update a corresponding miniport filter database. The filter database is located at the xfilter structure, which is addressed by 4 fields in the miniport structures. The miniport structure is called in this miniport adapter, this miniport block. The xfilter structure has one interesting field called the open list. This is a list. This is a single linked list of x-binding infrastructures, and these structures are actually contain our pointer to the just registered in this open block. So you see that this does not use this protocol list to find an open binding on any network event. But firewalls think that this does so. Firewalls walk the list of protocols in assumption that every protocol which will be found in the list can get packets to from the network, and the known other protocols can get the packets. So you see here that NDIS saves information about bound NDIS open block in the particular NDIS miniport block using a direct pointer. And to manage received packets, packet indication code will call these two functions. ETH filter DPI indicate receive packet or ETH filter DPI indicate receive. The second one is for legacy miniports. And then the packet managers will work ETH binding info list. And you see that NDIS doesn't care about NDIS protocol blocks here at all. Therefore, NDIS may indicate packets to the protocol which is not present in the NDIS protocol list. So it may be just excluded from this list after registration. But if this protocol is excluded from the protocol list, a firewall which works this list will not notice this protocol, so it will not be able to hook it. There are four approaches to bypass firewalls that use protocol walking techniques. These approaches are targeted to somehow cheat firewall and register a protocol that will be not present in this list, protocol list head. First two approaches use code pullout and some kind of direct kernel object manipulation methods. And the other two will not use any protocol registration. They will just hook existing ETH binding info or register a new ETH binding info structures manually. The first approach is about protocol unlinking after the registration has succeeded. First, a rootkit has to unhook NDIS registration protocol and NDIS open adapter functions. And after the unhooking has finished, a rootkit will have to call these hook-free APIs to register and bind the protocol. So this protocol will exist in the NDIS protocol list. But then rootkit unlinks this protocol because it already knows the NDIS protocol list head, and the information about address of NDIS protocol list head is required here because this list is single linked, and we cannot find the head of the list by working the list upwards. The major shortcoming of this method is that firewall may detect and hook newly registered protocols before we unlink it. So this solution is easy to implement, but it's not practical. The second approach is about modifying our copies of NDIS register protocol and NDIS open adapter. So they will look just like original functions, but our copies of these functions will address a different list head of the protocols, which will result in registering a protocol into a different list. So if we have a protocol which is registered in a list different than original NDIS protocol list, a firewall will notice nothing when it will check the list after the registration. This solution uses disassembler engine, so it requires, so it's not easily portable. And the other thing is that it requires to hook receive handlers of all other protocols bound to same adapter. Because we don't want our packets to come to original TCP IP stack. Other protocols may be hooked by a firewall, and we don't want the firewall to receive these packets at all. Next solution is to patch the X-filter structure. We will find the X-filter list by looking into the this miniport block structure for example, Ethernet data link layer. We will choose random protocol binding to the specific adapter by walking its open list links. Then we will make a copy of NDIS open block, which we choose randomly, and then we will patch all needed handlers in this open block and substitute a pointer to the original in this open block for the pointer to the patched copy. So this will result in tricking the packet indication code so that when a new packet will come to this code, the indication functions will use our and this open block structure instead of original. So this solution is very stealthy because it requires only one pointer modification. And integrity protection driver, for example, should check the X-filter for a single pointer modification. This will result in lots of false positives. The last approach is about emulation of the NDIS API code. If we register our own ETH binding info or X binding info structure without any original system code, we will be sure that no firewall has caught the registration because we don't use any system code to do this. The major shortcoming of this method is that it's very NDIS version dependent. So the receive packet techniques are more or less clear now, and I'll move to stealth packet sense. For the first two solutions, packet sending is trivial because all our structures, like in this open block and in this protocol block, are not hooked by firewall. So we will use pointers from these structures, and we may be sure that these pointers are not hooked by a firewall. Actually, the sending packet functions are defined in this with a similar names, like in this msendx and other ones. I show it. And these pointers we get from the send handler pointer. By the way, these APIs may be hooked in this image, so it's a good idea to use code pullout again. But we may not change any relocations because we will use original in this code. The third solution requires a different method of sending packets silently because actually we didn't register our own